And we'll now welcome our second speaker, Marcus Frank. Marcus Frank studied physics in Erlangen, Germany, and was exposed to the physics of optical interference coatings while working for your PhD at the Fraunhofer Institute for Applied Optics and Precision Engineering in Jena. Subsequently, he was internationally active for multiple employers in the field of large area coating, designing and developing coating products and processes for the architectural and automotive markets. Since 2018, he is responsible for R&D and applications in the market segment glass at Bühler Leibold Optics, Alzenau in Germany.
Okay, good morning, ladies and gentlemen. Thanks a lot for reaching out that early. To watch this presentation. I'm talking about patterned architectural coatings for large area glass facades and potential applications. So we did some work in the last couple of months, which is worthwhile to be presented. What I want to go through is actually how to pattern coatings, how to bring a pattern in optical coatings. And this, of course, you can do with a lift-off process. And when you hear lift-off, you think more of microelectronics or micro-optics. So I will start out with this and point out then how can we get then to the large area. And subsequently I will introduce the iterative lift-off process for architectural applications. So we bring some color into the facade. We'll go through the whole process steps, coating design, experimental procedure, and present the results. And then it's a little bit visionary, PowerPoint engineering, what could be the potential architectural applications. And I will conclude with some next development steps. Unfortunately, or fortunately, there's still a lot of work to do. All right, if we start with the lift-off. Classical micro-optic or microelectronic lift-off process works with microlithography. So we have deposition of the photoresist layer. Typically, it's by spin coating. Next step, you mask your sample, could be a contact mask or a projected mask. And then you expose your photoresist, you do the development, so you dissolve it in the exposed areas. And then you can actually already start with the PVD coating. So you overcoat the photoresist and also the gaps in between, so to hit basically the substrate, the glass. And in the final step, you do the lift-off process. You strip off the photoresist and, of course, the layers sitting on the photoresist. And as a result, you have a patterned PVD coating. Typically, the resolution here or the minimum feature sizes are around 5 micrometers. So this is points it out. It's micro-optics, microelectronics, so the features are very small. What can you do? Just a couple of applications. First of all, some SEM micrographs, so you see the feature sizes. In the upper picture, you see a sample with some 20-30 layers, typically tiox and silicon oxide, to get a certain spectral characteristics. In the lower picture, you see you can also repeat this process and put filters side by side. And this you can do also 3 times, so you can do something like RGB filters and stick those to a CMOS structure, as you see in the upper right picture. And then you can create something like a color sensor. Or you can really go directly on wafer scale directly on a CMOS structure and put your coatings directly on the receiving structure. And don't do a mistake, because then you mess up the whole wafer with a lot of elements on it. Okay, small sizes, and now how do we get this lift-off process to patterned large area glass coatings? So obviously microlithography is not the process of choice. Yeah? So also just think of spin coating of a jumbo. Yeah? Good luck. So we need to change the process, and actually a lot of technologies made a big progress the last decades, and these are printing technologies. So we can actually start with printing the mask. So I can basically skip all these photoresist procedures. So I directly print the masking material on the glass. And there are really good established printing technologies out there. So typically screen printing, which is very, very well known in the glass industry. And also digital printing, also already known, but still evolving, especially when it's about large areas. Next step then, again, PVD coating, put it on the mask material, lift off, or call it here wash off, because we really need use washing machines in this process. And then we have a patterned PVD coating. And in this place, depending on what feature sizes you want to have, but the smallest feature sizes is more like in the area of 100 microns. So larger, but we can also go then on larger areas with a printing compared to the microlithography process. What are the applications here? Just for one step, and this is not an architectural one, it's an automotive one. So this is also applied, this process in the automotive industry. Again, automotive windshield. We have areas there, so sensor areas in the automotive windshield, so rain sensors, traffic sign recognition, ambient light sensors, and there we don't need coatings. We want to actually avoid the coatings. So for this reason, they are masked off, so that we have here basically the clear glass without coating. And even more important, I cannot use the pointer, are these areas here, so where we get the actual silk print on the windscreen in the subsequent step, and these frits typically don't stick to the coatings, to the low E coatings or the IR reflecting coatings on a windshield. And for this reason, we need this to have coating free, so that we can apply this classical silk print and burn-in process. Okay, so now I want to introduce you to the iterative process. So before, it's not very colorful. Now I try to bring some color into the game. So in the iterative process, it's basically, we repeat it, and we use different filters, so different coatings. And now I introduce really the coating we finalized. I have a physical sample with me, 30 by 30, still a little bit small, right? But this is just for transporting reasons. So if you like to see it afterwards, then please approach me. So we did the following steps. So we did a print pattern, the first masking, basically. Then we put down just the opaque chrome layer, so just 70 nanometers of chrome. In the next step, we did the wash-off, lift-off process. Then we have a patterned chrome coating on the substrate. So this was the first iteration. And now we just go back to square one, do the same, but of course we use a different mask, different masking pattern. So as you see, we also mask off the chrome layer partially, and we mask off also a certain other part of the glass. And then we put a dielectric coating on top, so to get a nice interference effect. And this was really just done for demonstration reasons, no special spectral characteristics behind, so we just did this especially for this event today, right? So we put this coating on it. It's just a 3-layer coating. We see it in the next slide. And we do again the wash off, mask off, lift off, and we get a sample like this. So in fact, we can achieve with these 2 iterations 4 areas. So we have the dielectric coating on top of the chrome. So I go left to right. So we have a nice reflective color there. Then we have just the chrome layer, which is boring, just a mirror, right? Then we have in the 3rd area, we have the dielectric coating directly on glass. And in the 4th area, it's just the bare glass without any coating on it. So now we can think of how do we design it, and this was not a very extensive design work. We just wanted to minimize the dielectric layers and just get some distinct colors we can observe. So we just decided for a 3-layer coating here, so high, low, high, typical to get some colors into it and some spectral changes. Tiox, high index, low index material, high index again. And this was what we were aiming for. So you see the spectra. But more important, the colors in the table below. So here we basically have only a reflective color because the chrome layer underneath this dielectric stack is opaque, so we cannot look through. So we get a nice reflective bluish color. So you see the bluish greenish. So you see A star of -33, a B star of -12. This is really very distinct blue-green. Chrome layer, again, it's basically the backside reflectance, which you see also in the diagram here. Yeah, it's just around 40% reflectance, like a mirror. In the second area here, we have actually a transmission color and a reflective color with a dielectric coating sitting directly on the glass. So we achieve here a very greenish, very yellowish color in reflectance, very distinct. And in transmission, you find, yeah, of course, because we have no absorption, you find the complementary color, which is blue. We have a little bit of difference in absorption, as you can see here, but this is just due to the in reflectance, and this is due to the raw glass absorption, which plays a role here. So this is actually what we planned for, and now we really go through the experimental steps. We do the silk print, so you see this red fluid. This was basically this screen printable solvent based on a photoresist. So mask thickness after drying was aimed to be 12 micrometers, and we saw before. So we have a very thick mask, like 12 in the micrometer range, but we are in the nanometer range or 100 nanometer range with a coating. So it should be good, so that we don't cover the whole mask and have a good chance to lift off. And the next step is going to be dried, 15 minutes, 140 C, just in a box furnace, just all lab scale, of course, for the moment. And what we achieve are those samples. So you see the pattern we chose for the screens. Put our partners' names and our name also in there, and played around with a couple of geometric features and see how this works. And this is right before coating, so we see just the masking material, and after coating it comes out like this after the coater. So we put down the chrome layer, just one thick chrome layer, 70 nanometers, and you see the shiny areas is the coated glass, and the less shiny areas, this is the coated mask. And then we did the lift off, what I pointed out in the scheme before, and we got this beautiful result. Of course, not desired, so we had problems to wash off the chrome layer, and then we also removed basically the chrome where it should stick. So the adhesion of the chrome layer was really, really bad to the glass. So we went back, thought a little bit about it, and there is actually also a very well-known technology, which is a linear ion source in the vacuum coating right in front before you coat any layers. And this basically cleans off the glass surface. And since we have also the mask on it, it also will affect the mask material. So anyway, we tried this, retried this, and applied the linear ion source. So this was basically irradiated with ions, right? And then this is the linear ion source, and this is actually the process. This was a pure argon plasma at 1 kilovolt, and went through with the sample. And what you can see is actually here in this micrograph we finished actually afterwards. Basically the mask was also affected. It was edged off by basically half. So we have still 6 microns left in the masking material, which is actually still sufficient for our purposes for this design what we chose. So we did this again. So it was the coating, and then again, in the picture out of the washing machine, it's a little bit, it was actually a movie, and I didn't want to run a movie here because sometimes it's really problematic. And then you see in the next picture the result. And so this is actually what we want to achieve. So the linear ion source really helped here a lot to activate the glass surface and clean the glass surface, and the chrome layer got stuck to the substrate very, very well. So now this is basically the application of the second mask. You see it's kind of a little bit of a complementary pattern. So this was now applied on the patterned chrome layer. This is again right before we went through the coating, and now the next step, as you remember, is we put down the dielectric coatings, the 3 layers, tiox, silicon oxide, tiox. And this is how it comes out of the coater. So you have basically 3 areas. The yellow area, which is not so shiny, is actually the coated mask, the second mask. And we have coating on glass. You see this bluish area. This is basically transmission color you see as desired. It's bluish. And we have this coating on chrome, which is appears here as very dark, because there's no transmission, obviously. Yeah, and here we had also some challenges with the lift off again. Yeah, so you see the soak time was increased, and you see it's starting to lift off, but it was not as effective as before. And our main hypothesis is that the dielectric layer stack is much thicker than these 70 nanometer chromes. So we're talking about more about like 200 nanometers. But still, with some brushes, more soak time, and rinsing off, we were actually able to achieve the final sample, which was actually as planned. Yeah. Again here, so this was our stack, and this is the final sample. So you see this dielectric coating on chrome. This gives this reddish and bluish appearance. And this is not a non-uniformity that you see the same layer here reddish and here bluish. It's just a very strong angle dependency of the coating. This was not designed for very stable angle dependency. So this is not, just want to point out, this is not non-uniformity in the coating, because the coating is, actually the sample is only 30 by 30. And then we have the pure chrome layer in the area where all the company names are. We have the second coating on glass, and here you see the reflected yellow color, and we have also the uncoated glass where you can just look through and see the paper underneath. Yeah, just some data which came out of the SEM. We could actually also check the coating thickness. So it was something like 370 nanometers measured, and 313 was the design, so coating engineers did obviously a good job. And yeah, this was the process to finalize, to get patterned coatings on a piece of glass with different colors. And I think the key here is that now we are not limited to small samples. This is basically available for jumbo-size coaters, for jumbo-size glass. So in general, yeah, so there's some work left, what we need to do, but in the end there is no physical limits to go really on in the large area with this kind of processes. And as we can do this, and I need to point out, this is now PowerPoint engineering, what I do in the next slides. Yeah, so actually we could do something like this. You can put logos into a facade. Yeah, you can make crazy patterns in a facade. These are building integrated PV, so these colorful cover plates. Yeah, you can pattern those and put your logo into those coatings. Yes, I also used our name here in a building. Yeah, so this could also be done across multiple IGUs. Then of course you need a very good data exchange between the coating companies and the insulating glass companies. Yeah, so this needs to be planned and designed beforehand, especially when it's exceeding one insulating glass unit, when you write across multiple glass units. Another example, because I'm living in Frankfurt, right? So I could do something like this, or also an example out of Frankfurt. So Deutsche Bank building. You see the little logo here. This is actually the real one, which can be illuminated at night, but you can actually really get much bigger with applying these processes, hopefully in the future. Nonetheless, there's still some work to do when we go through this iterative process. So print the mask, PVD coating, and lift off. In the area, I think in the area of printing the mask, that's a wide field. Yeah, so we should actually switch over to, or take more into account the digital print. Yeah, because then we are much more flexible and we don't need screens for each and every pattern. And we need to identify the requirements for the printing material, because not every printing material is suitable for digital print. We need to improve the printing technology to achieve steep mask edges. And what do I mean with this? So I was always drawing the masks like this, like nice rectangles, right? But then you see actually the mask here, and it's really at the bottom. So this is the mask. This is the glass surface, this here is the mask, and you see the thickness here. So this is a really shallow slope here. Yeah? And now when you can imagine a thicker dielectric coating in a range of microns, maybe you cover this completely and then we have no chance anymore with lift off. So this is really a wide field we have to take care of. Of course, water-soluble printing materials would be nice, yeah, for environmental reasons, but also for the ease of removal. And yeah, minimizing the curing time is certainly then when it goes really into production, it gets important. In the PVT coatings, yeah, we can apply other filter designs, RGB filters. We need to improve. I mean, we did not take care of it, but we need to look into color stability so that the color does not change too much when changing the viewing angle. And of course, we also need to optimize the parameters from the linear ion source so that we don't remove the mask completely when we treat the glass surface. And lift off, optimizing the lift off procedure and the sample cleaning, so minimize the soak time. And of course, optimize the mechanical support. I reported that in the last step we had problems to remove the mask, and we can use brushes of different sizes, different pressures, and can optimize this. And also we want to test the ultrasonic application to remove the mask in a better way. This was my last slide, really just in time here, and I am open for questions. Thank you for your attention.